Hello students. So today we are going to learn something called Poisson process. And we are discussing Bernoulli process in my last lectures, and we ended that talk with something called Poisson approximation to the binomial distribution, right? So the question arises from there. So you remember in Bernoulli process, you have arrival. You divide the time interval into discrete time intervals, and then you know that in every interval there will be either one arrival or no arrival, right? But so this was this Bernoulli process. Okay, so now question is that it may be the case that the arrival is happening continuously, right? It can happen maybe somewhere here or here or here or here in continuous times, okay? But the number of arrivals are discrete, like one arrival or two arrival or 100 arrival, right? So then what happened? Then can you play the game of with the boundary process and find out how this kind of distribution happened or not? And the answer is yes, that we are going to take help from Bernoulli random variables and Poisson approximation to Bernoulli random variables, right? We're going to take help. So suppose the process started at some zero time and some time interval, say of length, say whatever tau, and we want to know how many such arrivals or success happen inside these time intervals. Okay. So these we are defining by the symbols. So we are defining by the symbols that p k tau is probability probability of exact probability of say exactly k arrivals during and intervals of length t or length tau. Okay, length tau. So this is this probability we are defining, and then we are interested to know that how this probability behave and whether given any time interval of length something, can you find out how many numbers of variables are happening or not, right? So those questions are natural question, and that deals us to define this new process called Poisson process. So we will introduce, so obviously we introduce a new, say, parameter, or rather say I can say positive parameter. I need positive parameter, say lambda to be, what is lambda to be? So we refer this we refer to as the arrival rate or intensity of the process. Okay, so with this we will define what do you mean by a Poisson process. Poisson process. Okay. So now let us define it. So definition. Poisson process. So an arrival process is called a Poisson process with arrival rate lambda, or we can say only rate, if the following happen. So what are the following things? So number one, it is called independence property. Independence property. What is that? So the number of arrivals during a particular interval. So let me write down, then I will explain it. The number of um, arrivals during a particular interval is independent of the past, or independent of the, or maybe you can not only past, even future also, independent of the history of arrivals outside that intervals. Arrivals outside these intervals. Okay, so geometrically, what does that mean? So we have an interval, say this of length, say tau, and you know there are, if you know that there are some certain number of arrivals here, say k many, right? So this number does not depend whether there are arrivals this position or this position or not. Okay, clear? If you have choose some interval which is outside of your chosen interval, then this number of arrivals independent with the number of arrivals outside this interval. So this property is called independence property. Okay, and then number two is called time homogeneity. Time homogeneity. Okay, so what do we mean by time homogeneity? So let me write down first. So the probability p k tau, what I define already, that of k arrivals, okay, is the same always if you choose the same interval time. So same for all intervals of the same length tau. Okay, so what does that mean? Suppose you have a length of interval tau here and something here, or maybe something here also. If the length of interval is tau always, then probability that k many arrival happened is same here. It is here also same, it is here also same. Okay, the probability won't change, but that does not mean the number of arrival will be exactly same, right? Probability of arrival are same. Okay, so this is called time homogeneity. So it doesn't matter where the time start from, the beginning or middle or the end. It can be in the beginning also, middle, end. If the time length is same, then probability of occurrence of k-many arrivals is always same. Okay. So number two property, and number three is very important property. It's called small interval probabilities. Small interval probabilities. Okay, now if you choose a small interval, so let delta is be length of a small intervals. Okay, and then probability that in that interval of delta t there will be no arrivals, zero arrivals. So this is this has, so this is a function of this is a function of delta. Okay, depends on delta, and when delta is small, then this quantity has a Taylor series function. So it is of the form lambda times delta plus higher order term of delta. So what does that mean? That means so maybe delta square and other things, or higher term, and that term tends to zero as and delta tends to zero. Okay, and so these are the Taylor series. Okay, and the probability that there will be one arrival having Taylor series function of this form lambda times delta plus the higher order term of delta square. This also tends to zero as delta tends to zero. Okay, so in other words, you can say that it is little o of in mathematics we use these symbols also. So these are functions. So this is a function. This is a function of delta, and suppose this function is say f delta, and this is say g delta. This function or f dash delta. So they are very small compared to delta. So what does that mean? That means we write down f of delta is little o, not big O of delta. So this means that is the limit delta tends to zero. This over delta, this is zero. The limiting value is zero. Okay. Similarly, for f dash also, f dash of delta is also little of delta. Okay, clear. So in the small neighborhoods, what does that mean? Small time in neighborhood, there will be at most one arrival or zero arrivals, because the no arrivals will be so what will be the more than, so this implies that if probability of, now you know that probability of all arrivals. Okay, so let me write down the next page properly. Now note that given any time length delta, so this sum of probability of k delta k equal to 0 to infinity, this is 1. So in any time length there will be either 0 arrival or 1 or 2 or dot dot dot, dot, right? This is one probability, and from that, from the previous thing we already learned that um, from the third property, what we learned that whenever k is greater than 1, so this quantity is 1 minus k delta, k is 0 and 1 delta, right? Either 0 or 1, because we are starting from 2 here, and so this is approximately, if we use Taylor series, this is 1 minus lambda delta and then minus lambda delta, uh, right? So what does that mean? That means this is approximately 0. So approximately there would be 0 arrival in the small time intervals. Okay, this is the meaning of third statement. Okay, clearly. So so if some process satisfy these three conditions, condition number 1, 2, and 3, then we call it is a Poisson process. So independence property tells you that given any time interval, the number of arrival does not depend on whatever happening outside the time. Then number 2 tells you that if you take the same length of time, the probability of k many occurrence or k many arrivals is same, and that probability tells you the small probability will be this, right? So by this we define the Poisson process. Now let us try to understand that how we will be finding this quantity, probability that k delta, k tau, whatever. Okay. So let us try to find out. Mm, so whatever interval is given, so we have an given interval, say tau. Okay, so what we'll do, we will divide this interval into small sub intervals of delta length. Okay, so that from third property, the probability of parent more than 1 is neglected, 0 almost. Okay, either 0 arrival or 1 arrival, right? And then so after doing this, what we will do, we will write down so if we so how many pieces we will have in here, so number of pieces, so we write down that number of pieces is tau or delta. Okay, so we can think this is number of pieces here. Okay, and delta is very small quantity, and each of those small time length delta, there will be at most one arrival, right? So property 3 tells me this, and what will be the probability of arrival? So in these small intervals, so I can write down this as probability that 0 arrival will be 1 minus lambda into delta, and probability of one arrival, it will be lambda delta, right? Approximately. Okay, so now we can think that this is kind of a so this process can be thought of as a continuous version of, or continuous analogue, whatever. So continuous version means continuous time version or time analog of, not the number of arrivals. Number of arrivals is discrete always. Here also Bernoulli process So what we can do, so we can use Poisson approximation, right? So we can think this is a Poisson approximation and to these things. So here your n, so you divide into small intervals such a way that length is delta and probability of appearing is nothing but lambda delta, where lambda is the rate of the process. Okay, and so number of n is what? So n is, so this is your probability, and n is nothing but tau of delta, tau by delta, every length is tau. So np was what? So you see n is large because delta is small, so n is large and delta is small. um, but np, which is nothing but um, uh, tau by delta into lambda delta, which is nothing but lambda tau, right? So lambda tau is moderate. Okay, so mt is moderate. So now Poisson approximation tells me that then if we choose the number of variables, so let me write down. Okay, so then this probability that in the there will be many arrivals in length of time tau, that will be what? That will be satisfying the Poisson distribution with parameters np, np equal to lambda tau, and this is nothing but lambda tau to the power k e power minus lambda tau by k factorial, and k can be 0, 1, 2, and okay. So this will be the probability. So we already find out the probability is that. Now we can check that whether this satisfy the important third condition. So what was the third condition? So condition 3 of the definition. So we need to check that whether p0 tau has a Tapas function. So what is the Tapas function for this when k equal to 0? It is nothing but e power minus lambda tau, and Tapas is nothing but 1 minus lambda tau plus c higher order of tau square. Okay, which is obviously this portion is tends to 0 as tau tends to 0. Okay. Similarly, probability of 1 tau, 1 arrival is what? Is lambda t, lambda tau into e power tau lambda tau, and this is nothing but lambda tau and plus higher order term in tau square from here, right? So you see that this probability law actually satisfy the condition of okay. So where I define the condition? Yeah, yes, yeah, this condition. Okay, small time interval condition. So this is actually that probability is satisfying my Poisson process. Okay, and now if we define this random variable, so now let so n tau uh, be the number of arrivals and number of arrivals during during a time interval time interval tau. They satisfy what? They satisfies Poisson PMF, right? Poisson PMF. And hence the expected values of these we know already for Poisson PMF. Expected values is nothing but lambda tau, and the variance will be nothing but lambda tau. Okay, this is already learned from our previous things. Okay. So now so there are one more thing. So this is what number of arrivals during time t, time length t, that is Poisson. So this in tau is Poisson with parameter. What is parameter here? The parameter is lambda tau. Okay. Clear. Now what about inter-arrival times, like time between first arrival, starting from 0 to first arrival and the second arrival? So we can ask this property. What about this? Okay, so let me first ask the first arrival. So how the first arrival look like? So uh, this is first. So let us do it. Then we will go to next stage. Okay. So um, let t be the uh, be the time of the first arrival. Okay, so t is a random variable. We need to find out uh, how t look like. Okay, now see, arrival time is continuous. You can understand the arrival number of arrivals is discrete, but arrival time can be anywhere, right? Continuous, it can be here, anywhere. Okay. So we need to find out the density function here, right? So to find out the density function, it is first easy to find out the distribution function. Okay. And we are assuming that okay, so let so the cumulative distribution function of t. So what will t? This will be, write down f of t at t. So what does that mean? That means this is probability that t less than equal to t, and then we can find out this is nothing but 1 minus probability t greater than t small t. But what is this? This probability that capital T greater than small t. So that means the first arrival happened after capital T times. So that means there is no. So this means this is the probability that from 0 to t intervals there are no arrivals, right? Then only the first arrival came after t, right? So this is equal to nothing but p 0t from our definition phi kt. Okay, so in time interval length t there are zero many things, right? Zero many arrivals, and that gives us f of t at t is nothing but 1 minus. So what is the zero arrival? So zero arrival from now from the definition from this formula pk tau equal to this, right? So instead of k equal to, if you put k equal to 0, so you will have pk t equal to e power lambda t. Okay, and k equal to 0, so k factor is 1. So it is 1 by e power minus lambda t. Clear? Whenever t is greater than equal to 0, the positive time. Okay, now if the density function is of this form, then the PDF probability density. So this is the distribution function CDF. The PDF of T is and the derivative of this side. So PDF we can write down as derivative of this, which is nothing but lambda times e power minus lambda t, t greater than equal to 0. Okay, now it is clear to understand that it is nothing but a, so thus t has an exponential distribution, or so t has an exponential distribution okay with parameter lambda. Clear? So the first arrival time is nothing but uh, exponential distributed with parameter lambda, and the number of arrivals in any length tau is with parameter lambda is defined by a Poisson variables, okay, with parameter lambda tau. So what is that? So whatever we discuss, what is the gist of our discussion? So we can write down as a um, chart. So kind of so okay. So we have Bernoulli process. Bernoulli, okay. Just let me write down Bernoulli only. A Bernoulli process, and then we have Poisson process. So here is the time of arrival. In Bernoulli process, time of arrival was discrete. Here it is continuous. It can come anytime, right? And then PMA of arrival, that mass function. So if we choose the arrival satisfy discrete many arrivals are happening, so PMA of number of arrivals. So this is binomial. Remember we have done binomial, and this is Poisson. Okay. Now what will be that the first arrival or inter-arrival? I will come also. Both are same because they are independent. First arrival time or inter-arrival time also. The time in this case, this is geometric, which is also a discrete random variable, but this is no longer discrete. This is become continuous. So this is exponential. Okay, and then arrival rate. So here you have this probability per unit per trial. For each trial the probability is this, and here lambda per unit time. Whatever you choose the unit time, small interval. Okay. So clear. So by this way you can actually distribute two such um, process, manual process. So let us start with one example, then we'll have more understanding on this process. So okay, so suppose Okay, so suppose so so I am receiving emails um, according to a Poisson Poisson process rate. Was at a rate say lambda equal to say 0.2 message per say hour. Okay, and I am checking emails, so I am checking emails every hours. Every hours. So what is the probability that what is the probability of finding what is the probability of finding either 0 or 1 or 0 and 1, 0 message and 1 message, 1 new message. Okay, so this is a process. I am getting things, and then I am asking what is the possibility of getting either 0 new mail or 1 new mail in 1 hour, right? 1 hour time duration. So now, so solution. So this is obviously process. You know that, and that the PMF of arrival PMF is lambda tau to the power k e power minus lambda tau by k factor, right? Now here lambda equal to 0.2 and tau equal to 1 hour. Okay. Now you can find out what is p0 1 tau equal to 1, and then you find out k equal to 0. So this is e power minus 0.2 whatever value is, and then 1 is 0.2 power 1 and e power minus 0.2. Okay, whatever is the value. So these are the rate. Okay. Now suppose I did not check. Now suppose I did not check and then my message for whole day, to 24 hours. Then what is the probability that of finding no new messages? Okay. So I am asking if I don't check message for 24 hours. So time length is 24 hours. And then what is the probability that there will no new message? So 0 new message. And that is will be nothing but e power minus. Here now tau equal 24. So it is 0.2 into 24. Okay, whatever is the value. So that value is right. And so by this you can ask similar kind of question. Okay, so now if you can sum two random variables. So suppose or maybe let us first tell you some of the properties, and then I will come to another sum. Okay, so what are the properties we can get here? Properties of So process. Okay. So the first property, independence of independence of non-overlapping overlapping sets of time intervals. Okay. So what does that mean? So suppose we have uh, time interval, we have a set of time here, say A and something B. Suppose they are non-overlapping, and then you have random variable which is counting the occurrence of or arrivals here. Suppose this is my x1, this is x2 occurrence here, this, then this x1 and x2 are actually independence. Okay, and this is coming from the first property. So then this implies x1 x2 are independent, and this is coming from the first property of the definition. Okay, and then there is similar. So we have a fresh start property in Bernoulli process, because this is kind of a coming from a Bernoulli process continuous time interval analog. So we do have a fresh start property here also. So we can have fresh start property. What is that? So it tells you that suppose you have an arrival here somewhere, okay, and then you are waiting for the second arrival. The second arrival can be anywhere, and this is again having the same property. So it is also the independence property also tells you that after first arrival, the second arrival also satisfy the same property, and then so on. Okay. So every time you got a arrival, and after that time you have a new fresh start, and that does not depend on your previous or your future times. Okay. So fresh start property tells you that this inter-arrival, whatever I was asking you, that inter-arrival times, inter-arrival times. So this is T1, T2, and so on. Times are also dependent and having exponential distribution. Exponential distribution. Okay. So the fresh start probability tells you the interval time is of this form, and now memoryless interval time distribution. So this is another property. So let me discuss what is this. The property 3, memoryless interval time. The interval time is also memoryless following the memory distribution, and this is also so this is we already learned in our previous courses, the exponential distribution and memoryless property. So that means what? That means we want to find out what is probability the time of arrival is t plus s more than t plus s, given that it is more than t. and so you know that there is no arrival before t, then what is that probability that it will be more than t plus s, and then it is nothing but conditional probability, nothing but probability that t greater than t plus s intersection with t greater than t, and then given probability of t greater than t, right? And then you see that the numerator is nothing but probability t greater than t plus s, denominator is t greater than probability of t greater than t, and you see that in numerator you have e power minus. So this is the first success interval times lambda plot this, and then e power minus lambda of t, and it is exactly equal to e power minus lambda s. Okay, so what does that mean? That means that yeah, so in the time length of from t to, so this is t plus t plus s plus, so this time length s does not depend on t. This is always same as, this is always same as probability that t greater than s. Okay, clear? So so this interval time has this memoryless property, which is already we learned from our previous sections. Okay, and so what does that mean? That means um, you can also write down, or you can also um, okay, so maybe I can give you one example and then we will stop here. Okay, so examples, so when you enter a bank you find out that or maybe I can just stop here, so we can do this kind of example for our next lectures, okay, as a part of quiz or something. Okay, so here what you will learn, so what is the gist of today's talk? So the gist is that when the arrival is not discrete, it is continuous, then we can extend the Bernoulli process to Poisson process using Poisson approximation. Okay, and we need to define it properly using three properties. Okay, independence property, time unity, and small interval properties. Okay, and then we find out that the first property is number of variables in a given time slot or time interval length tau with rate lambda is satisfying a Poisson distribution of parameter lambda tau, and the time of first arrival satisfy the exponential distribution of lambda. Similarly, inter-arrival times, like time between any two arrivals, is also satisfying the exponential distribution. Okay, so this is the most important property, so we learn. So I will stop here. Hope you are reading my previous classes. In next class we will learn more properties and with more examples. Okay, so we'll stop here.